Now we're going to revisit the general multiplication rule. We just had the multiplication rule at the beginning where we just said, oh, probability of A times probability of B. Well, the interesting thing is now we can actually accommodate dependent events, so the conditional events, by slightly modifying the equation we just had. So if I go ahead and say probability, remember this was on the left side of the equation, and I multiply both sides by the denominator, I get probability of A and B equals the probability of A times probability of B given A. And you can also do the same thing because if I do probability of A given B, the B comes up here because it was in the denominator. So for any two events, I can do that. It always works. And it takes into account when things depend on each other. Now, independence of two events means that the outcome of one event does not influence the probability of the other. All right. So our new notation, we can formalize this and say that events A and B are independent if the probability of probability of B doesn't really depend on A. That's just the probability of B. Okay, so whenever these are the same, or probability of A given B is the same as A, then the events are independent. So let's revisit our example from before. I've got a table of students wearing jeans in a class, and are sex and attire independent in this class? Well, the probability of wearing jeans is roughly 33%. The probability of being a male who wears jeans is about 71%. So the probability that you are male, that you're wearing jeans given that you're male, is not the same as the probability of jeans. So for this case, males are more likely to wear jeans than students in general. So these are not independent. Now, don't confuse independent with disjoint. Disjoint events cannot be independent. Okay, wait a second. What are we talking about? Remember, disjoint means mutually exclusive. They cannot happen at the same time. Since we know that disjoint events have no outcomes in common, knowing that one occurred means the other didn't. So if I knew I drew a king, then I know the card's not a queen. All right? But if I drew a king and ask you if it's black, there we got something to work with, right? But if I ask you, what is the probability the card is a queen, given that I drew a king, you can automatically know that, hey, it's not the same thing. So the probability of the second occurs depends on our knowledge of the first. So the two events are not independent. So disjoint, mutually exclusive doesn't mean independent. So don't treat them as they were and apply the multiplication rule for independent events, okay? So don't make that mistake. So let's go ahead and go back to drawing without replacement because that's a really common example in dependent events. So sampling without replacement means that once the individual is drawn, it doesn't go back in the pool. We frequently sample without replacement because we're like, oh, we want to have different data points in our sample. And it doesn't matter too much for us normally when we're dealing with a large population, which we tend to do in statistics. But since we also cover probability, we need to take into account when we're drawing from a small population and adjust accordingly. So this is another instance of working with conditional probabilities. So first of all, let's look at which events are dependent or independent. So I'm just looking for dependent, where the probabilities change depending on the first thing happening. Drawing a marble from an urn, replacing it, and drawing a second marble. Well, if I put the marble back in the urn doesn't know, it's not going to affect how I draw my second one. So those are independent, okay? Replacing it keeps it independent. If I roll a die and draw a card, the card doesn't say, oh, okay, I need to change because of the die number you rolled. They don't know anything about each other. They are definitely independent, all right? So they're not dependent. Now, if I draw two marbles from an urn, so I'm keeping both marbles, I have limited the pool for my second marble. So drawing two marbles from an urn is dependent. The second marble's probabilities are going to depend a little bit on what I drew on the first one. Kind of like drawing, if you did poker, drawing two kings. So that one's going to change if I keep the cards. If I don't keep the cards, that's different. Rolling a die, so that one is dependent. It is not independent, it is dependent. So that's the kind of problem we're talking about. Rolling a die twice, well, your die better not know what's happening between them, or they're really strange dice. So anyways, that is totally independent. So let's take a look at an example and calculate it. So I've got a 52 cards, 4 of each type of card. Determine the probability that 2 jacks are drawn from a deck of cards without replacement. So I want the probability of a jack and a jack. Well, the first probability is 4 out of 52. But look what happens to the second probability. It becomes 3 out of 51 because there are 3 jacks left out of 51 cards. Now, I'll just go ahead and do the rest of the math, simplify. And so that probability would be 1 out of 221. And odds are we would give a decimal answer on our AP test. All right, I have a partiality to fractions myself. A jar has 3 blue marbles, 2 red marbles, and 1 yellow marble. So we have a very small sample here. Calculate the probabilities that a blue, then a red marble are drawn without replacement. And notice how I'm giving you the order here. All right, so the probability of a blue, well, there's 6 marbles. That should be 3 out of 6. But when I take out that marble, my total number of marbles has changed to 5. And there are 2 red marbles left. So I can say the total probability is 6 out of 30, which is basically 1/5.